Okay, recording, cool. So yeah, we're recording. As I say, any problems hearing us, let me know. If we have any problems hearing you, obviously, especially when you do your talk, Kat, so we will let you know. Any questions or anything, just shout out. But yeah, otherwise, let's get started. So I'll try and stand roughly on camera. Can you see me? Yes. Okay.
You want to spin the TV, but
Spin the TV.
Yeah.
There we go.
It's an idea.
That is an idea, Rich. What you here for? Yeah. So welcome everyone. Thank you for joining us for the first time. Thanks everyone for joining us online. So I'll just keep it brief. Just want to say this is our second in vivo event-driven architecture tech event. We're hoping to continue doing these every first Thursday every month, roughly, but might change here and there, but roughly the first Thursday every month. Anyone would like to give a talk at a future one, let us know. We're interested in anything who's, people who are new at the event-driven space, who are just getting into it, or people who are experts. So obviously, we're eager to hear about everyone. Yeah, thank you to Rich and Vigo, obviously, for all who are hosting this for us. Giving us a space to work from. Obviously, great to have somewhere to do this in central Manchester as well. And yeah, that's pretty much it. Any questions, let me know. If you're in the office, have some food and beer. There's drinks and things in the fridge as well. Toilets just at the back, if anyone's seen them. But otherwise, I will hand over to our first speaker, which I believe is Kata. So thank you, Kata.
Thanks, Jamie. I will quickly share my screen. Please let me know if you can see this. Can you all see this right?
Yeah, looks good, Kata.
Okay then, so good evening everyone. My name is Kata Sas. I am a junior developer at InVivo for almost 2 years now, and I'm joining this meetup from my hometown in Transylvania. In this session, I will give you a quick introduction into Kafka Streams, and then we'll compare global state stores with local state stores using RPC in Kafka Streams applications. As I said, let's start with a quick introduction into Kafka Streams, just to make sure everyone gets familiar with the main concepts. The modern programming landscape has exploded with big data frameworks and technologies, and with this, we need to process more and more data every day. As the amount of data grows, the need to analyze and take advantage of the benefits of that data grows at the same rate. Having the ability to process large quantities of data in bulk, which is named as batch processing, isn't always enough. Increasingly, organizations are finding that they need to process data as it becomes available. That is named as streams processing, and this is where Kafka Streams come in. Kafka Streams is a cutting-edge approach to stream processing. It is a Java library that allows you to perform per-event processing of records. Per-event processing means you process each record as soon as it's available. With other words, stream processing is the ability to work with an infinite stream of data with continuous computation as it flows, with no need to collect or store the data to act on it. However, I mentioned Java, but we use Kotlin at InVivo to implement Kafka Streams. They once took Java to add and added to it every nice feature that was missing, and then when they finished, they called it Kotlin, so we couldn't choose anything worse than that. Although any JVM language works well with Kafka Streams application, like Kafka itself has clients for most major languages. This is a very simple marble diagram representing stream processing. Each circle holds some information or is an event occurring at a particular point in time. Here, the number of events is unbounded and moves continually from left to right. This ordering of events is part of Kafka Streams. Unbounded means that we don't know the number of events, and the number of events is unlimited. Let's quickly go through on an example before we move on. Imagine a situation where Tom buys a TV and he pays for it with credit card in a shop named TV World. When Tom is walking out of the store, he gets an SMS from TV World thanking his patronage with a couple of coupons for his next visit. Going through on the business requirements, we can create this directed cycle graph representing requirements for the streaming application. The point where Tom completes the transaction at the register is the source node of the entire graph holding sales transaction information that will flow through the graph, where the requirements become the child nodes of the main source node. Once the purchase has happened, a masking step is needed for security purposes when the credit card numbers gets protected. For this making operation, we copy the raw data from the parent node and we convert it into a protected form. The data flowing through the rest of the graph will have the credit card numbers converted and protected. The next node is the patterns node, which instead of copying the data received from the masking node, it only extracts relevant information to establish where customers purchase products throughout the country. The next child node is the process is the rewards accumulator. It extracts the amount spent and the client IDs and creates a new object containing those two fields. The final node is responsible for storing the data into a NoSQL data store for future analysis without converting it into any other format. Now, let's look at the processing graph again, but this time we're gonna create a Kafka stream program. In this word, we define a topology of processing nodes, where we can have one or more source nodes, which are Kafka topics. Just like previously, each node can define other child nodes, and each processing node performs its assigned task and then forwards the record to each of its child nodes. Here I mention then a Kafka topic is an unbounded stream of events, just what we mentioned with the marble diagram a couple of slides ago. Records flow through the topology in a depth-first manner, which means each record is a key-value pair represented by a key stream record, and each pair is processed in full by the entire graph before another record is forwarded through the topology. The first step in any Kafka Streams program is to establish the source of the stream, what could be a single topic, multiple topics in a comma-separated list, or can be a regex that can match one or more topics. In our example, we have one single topic named transaction. This topic holds the raw data converted into purchase object with information what you can see on the slide. Now that we have our source, we can start processing the data. Our first goal is to mask the credit card numbers in the incoming purchase record. The K-stream map values transformation method will perform the masking for us. The purchase patterns processor receives a purchase object and maps this to a new purchase pattern object that holds only the relevant information like zip code and the item purchased. Then adds a child processor node that receives this new object and writes it out into a Kafka topic named patterns, so other applications can then consume this information from that topic. The same thing happens on the rewards processor, as you can see it on that diagram, while the final processor is responsible for writing out the entire purchase object into another Kafka topic, and then the consumer of this topic will store the result into a NoSQL database for the future. Now let's have a look at this implemented in Kotlin. Custom serializers and deserializers have to be built, but here, as you can see, we just have a custom search to represent all the different certs we should have for simplicity. Then we first consume the data from our source transaction topic and we map it into purchase object, mask the credit card number, and then write it out into purchases topic. This write out bit, remember, this is the final child node from our graph previously. Then we map the purchase objects into purchase pattern objects and write it out into the patterns topic. Finally, we map purchases to rewards and save them into the rewards topic. Furthermore, you can notice that 1 out of 3 transformations has state, while 2 are stateless. The first 2 are stateless as the event contains all the data you need to perform transformation. So you just get the data from the topic and then you just transform it as it is and save it. While for the third one, to do the sum transformation, you need to know what events you previously processed, because otherwise you can't track the running total for each customer. However, creating state in Kafka streams from a stream is very easy, as it utilizes stream table duality. Stream table duality is a concept where an event stream can be visualized as a simple table. We can say a table is an abstraction over a changelog stream where the table shows the latest values for each key. More precisely, the value in a data record is interpreted as an update of the latest value for the same record key, if there's any. If the corresponding key doesn't exist yet, then the update will be considered as insert. Using the table analogy, a data record in changelog stream is interpreted as an insert update because any existing row with the same key is overwritten, while data with non-existing key is added. Also, a record with a null value represents a delete. These local stores are implemented by k-tables in Kafka streams. Now that we saw how Kafka Streams works, we can say that reaching or querying the data and storing or writing it out is a key part of stream processing. A Kafka Stream application could be dealing with billions of data or events every day, and to handle this big amount of data, they are typically running on multiple application instances for performance and scalability reasons. To handle it, each Kafka topic is really not just one unbounded event stream, but several, and each stream is called as partition of the topic. As Kafka partitions the data, the application's entire state is spread across partitions. When we query data from an input topic into a K table, then the table only manages a subset of these partitions, which is an important capability when implementing stateful operations, because each application instance can then manage only a subset of the data. Let's have a closer look at what was said just now. This diagram represents a situation where we have 3 running instances of an application, each of them running an instance of the Kafka Stream application against a Kafka cluster. As we can see, each running instance has its own local state store, and in this case, all those local state stores are just a subset of the application's entire state. Each instance can directly query its own store without any further effort, but it will only return data that is locally available on that particular instance. This causes problems when we need to compare data that is not co-partitioned. Example, from our payments example, if we want to compare 2 customers' rewards information, the data for those can be in 2 different partitions. So there are situations where we need to work with the entire state of our application, like with the whole topic, not only with a partition, because we need to analyze the data as a whole, like count or aggregate on it. In these cases, we have 3 options. The simplest option is to repartition your data, or we can use global state stores, or we can expose the full state of our application to other applications, including ones that are running on different machines. This one can be done by adding an RPC layer to our application. We're gonna focus on the latter two, but just to mention the repartitions, here is an example. If we want to do comparison to all customer rewards who are in the UK, it is very possible that those customers are in a different partitions. To collect them, we can restream them into a new topic where we partition them on country, and then we can do our aggregation. The downside of this is that we need to reprocess and duplicate the data, and depending on what we partition on, can limit our scalability. For example, to look at the data for the whole world, we can have only one partition to make our data co-located. However, global tables and RPC are also useful when we need to do any aggregations where the data is not co-located. First approach we're going to talk about is using global state stores. Instead of querying the topic partitions into a K table, we can query the whole topic into a global K table. Global K tables are global tables because when we are running our application with 3 application instances reading from an input topic which has 3 partitions, then each application instance's local store will hold the entire data from the topic, not only the data from one partition. This means each application instance has the same entire application state stored locally. This diagram is very similar to what we saw a couple of slides ago, but the local state stores are identical and all of them holds the entire state of the application, not only a part of the data. If we would like to implement global state stores, it would look something like this. Again, we should implement our own custom search to transform data from transaction topic to correspond the data structure we would like to see in the populated purchase store. The store we built here holds the entire data. In other words, the data from all partitions of the transaction topic is present in the store. So collectively, across all application instances, all input topic partitions are consumed by all instances of the application. Let's have a look at the pros and cons of global tables. Using global K-table instead of K-table means that each application instance can easily reach the entire data as it stores it locally. This provides us more convenient and efficient joins, and they also support star joins, foreign key lookups, and they are more efficient when changing multiple joins. Furthermore, global tables can be used to broadcast information to all the running instances of your application. It has the advantage of letting us treat a topic as it has one partition, which means data is always co-located. Although global tables require a full copy of every partition's data for each instance of your application. So if you're running 10 instances of your service, a global table needs to process 10 times the data. They also need to process all records before your stream application starts processing incoming events. This increases startup time and makes them non-deterministic. Another approach to work with the entire state of the application is to query it remotely. For this, we have to expose the application's full state, making it queryable to other applications, including ones that are running on different machines. Here we use RPC to communicate between services. RPC is a distributed computing technique in which a computer program calls a procedure, which can be a subroutine or service, to execute in a different address space than its own. The procedure may be on the same system or a different system connected on a network. At InVivo, we do RPC throughout REST API, and technically this isn't RPC, but solves the same problem the way we are most comfortable with it. These are the steps we have to go through to implement the aforementioned process. Add an RPC layer to our application so that the instances of our application can be interacted with by the network, for example, by REST API, as instances must respond to interactive queries. Expose the RPC endpoints of our application instances, which must be unique within a network to be discoverable by other instances. In the RPC layer, discover remote application and their state stores and query locally available stores, making the full state of our application queryable. Here is the diagram again. This time, each of the app instances use K-table to store only a part or partition of the entire data, and using a unique endpoint to expose their existence and make their state stores visible and reachable to other application instances. Now, let's go through on the 3 steps we mentioned and have a look at their details. There are many ways to add an RPC layer. The only requirements are that RPC layer is embedded within Kafka Stream application and that it exposes an endpoint that other application instances can connect to. Let's see how can we expose an endpoint. To enable remote state store discovery in a distributed Kafka Streams application, you must set the configuration property in the config properties. The application server property defines a unique host port pair that points to the RPC endpoint of the respective instance of Kafka Streams application. The value of this configuration property will vary across the instances of your application. When this property is set, Kafka Streams will keep track of the RPC endpoint information for every instance of an application, like its state stores, assigned streams partitions, URL details, and other application information through instances of streams metadata objects. Here is an example implementation of this part. The application server property is set to a unique endpoint value, and this way the store created below is now available for others to query it. Now, how can we discover exposed endpoints? To discover and access application instances and their local state stores, we use these listed methods, which returns streams metadata instances, providing meta information about application instances such as their RPC endpoint and locally available state stores. If application server property is not configured for an application instance, then the above methods will not find any streams metadata for it. Here you can see an implementation using one of the methods from the previous list. If it can't get the customer store, then it searches for the host and port for an endpoint which has the stored locally, and then it queries the endpoint to get the customer store data from it. If we have all of these three steps implemented, then this point, the full state of the application is interactively queryable. We can discover the running instances of the application and the state stores they manage locally. Throughout the RPC layer that was added to the application, we can communicate with these application instances over the network and query them for locally available state. The application instances are able to serve such queries because they can directly query their own local state stores and respond via RPC layer. Collectively, this allows us to query the full state of the entire application. There are a couple of advantages and disadvantages of doing RPC calls from within a Kafka Streams application. An advantage is that we can store our data in local tables, which means we store only a partition of our data. This means if we have a topic with 3 partitions and an application with 3 instances, then we store only the third of our data locally instead of the whole data. But having RPC implemented, we still have the whole data available to query. As we already know how to build REST API, it is easy for us to add an RPC layer into our application. However, this way we gradually move to event-driven architecture powered by Kafka. As we don't have to load the whole data, but 3 or 10 times less than the whole, our application startup time should be 3 or 10 times faster than with global tables. Now, there are a couple of disadvantages of doing RPC calls. One of them is that we are coupling the availability, scalability, and latency of our Kafka Streams application to the availability, scalability, and latency of the RPC services we are calling. Furthermore, an RPC call is a side effect and a black box for Kafka Streams. Let me explain this with an example. In the case of any failures, Kafka Streams will retry operations, and this will guarantee exactly once processing if it's enabled even in such situations. But we can't guarantee by itself that an RPC call we are doing from within like a map function will be idempotent. Ensuring this is now our responsibility. However, we can avoid it by making sure the procedure we are invoking are all pure side effect free functions. In fact, at InVivo, we follow a functional programming principle where we try to focus on side effect free function in our services as a general principle. Repartitioning so let's quickly have a conclusion. Repartitioning is good when the data just have to be grouped but still can be scaled. Global tables are good for small amount of data where we don't mind processing events multiple times. A good example for this is product types in our example case, as this data isn't changing frequently and it is a small amount of data that we can load and handle easily in global tables. However, data that has a large volume and we don't want to store or process multiple times, for example, the purchases events from our example, we should use RPC calls to allow us distribute load much more efficiently. As an experience at InVivo, we started with repartitioning of the data every time we needed it, but eventually we decided to introduce global tables for simplicity, and as we matured, we implemented RPC. And today we use all three options depending on the nature of the data and the corresponding service. So in this session, we thought about how Kafka Streams application can solve businesses' big data processing issues. Then we thought about repartitioning to co-locate data when it's possible. Then global state stores provides the entire data stored locally in each application instances. And by exposing local state stores with RPC allows to query the whole state of the application without storing the entire data locally. Thank you so much for your attention. I hope I could share something new and interesting during this session. And if you have any questions, please feel free to ask.
Awesome. Thank you, Kata.
Thank you,
Thank
Kat.
you.
Thank you.
Was there any questions, Kata?
I would like to ask what is an RPC a bit better?
Okay, do you want to
Sorry,
talk?
can you repeat that?
The RPC, that concept.
Do you want to talk a bit more about the RPC concept, Kata? I think the question was.
Oh, of course. So, like, if you have a big amount of data stored and you would like to query it, the first thing I was talking about was that you just query the whole data for each instances of your application as a whole. You store it and then you easily can reach it. But because the amount, the volume of the data is so big, storing it in each instances of your application can be slow. It can consume a lot of storage and it can be a lot of time for your instances to start up because they need to process the whole data before they can start up. Now, this is where RPC comes in, because with RPC, you still can store your data with local tables, and you can store only a part in each instance of your application can store only one part of that whole data. And then if that instance needs something else, which is not stored locally for them, then it can make RPC or REST API calls to other instances which are exposing their local state stores, and then you can get the data from there. So basically you don't have to store the whole data, you can ask it from the other instances of your running application. I don't know if it was enough. If you have any other question, please feel free to ask.
No, I don't.
I have a question.
Mm-hmm.
So do you mean that the apps are connected to one another via APIs and that they request data from one another depending upon
Yeah.
it, or need data from a different partition than the one that's
Yes.
for their own application?
Yes, exactly. So like imagine you have two instances of your application and you are working with customers, and then you would like to compare customer A to customer B, like on the first name. And then customer A is stored on instance 1, while customer B is stored on the second instance. And then to be able to compare that, instance 1 have to ask for that data for instance 2 via a REST API call, and then it can compare.
One of the big things in Kafka is, and especially when you're using it in like a scalable way, like we deploy in Kubernetes, you might have just 2 instances, like I was saying, but you could have 10 partitions. How they're allocated to those 2 partitions isn't necessarily known at the time you deploy the process. So you can't just say, go to this instance and ask it, because it could be 2 now, but there could be a spike of data coming later, and this means it scales out to 10 instances. So your API not only needs to know what data it has locally, it needs to know which of the 10 to call to get the data it needs. And that's what Kata was showing us with you can register with Kafka the metadata, and Kata showed us how you can go and ask Kafka, your name's too similar, ask Kafka what is the metadata, what is the metadata for the service, not just which service, but which specifically service do I need, what's the port and the host name. Yeah. So it does that kind of resolution of which API do I want to call for the data I need. So you don't just call all 10 and say, which one of you has got this data I need. Yeah.
Mm-hmm.
It does mean you have to scale a little bit more, because that one API call from your users potentially has to then hop to another node or another 2 nodes, but at least you're not going to hit all the APIs and say which one of you's got the data I need. Any other questions?
It would be interesting to know, is this kind of a mirroring mechanism for this data to get translated into kind of a backup server, or like what's the safety mechanism that is used by Kafka? Because I'm new to this.
Well, interesting. That's one of the problems we've been having actually ourselves internally is when one of the services dies and it's got the full state notification, it can take a while for one of the other services to build it up. So one of the things we've been looking at is standby replicas that are ready, so that if at least, and Kafka's recently introduced a new thing in one of the later versions where if the service that has the latest data goes down, it's able to use the replicas that might be a little bit out of date, but at least they've still got some data and something you can use, rather than saying we can't process it because the service you wanted is actually just gone down for a split second. It's definitely you get any difficulties when you start looking at obviously distributed data, but this is what Kafka does help you solve. One of the questions I had actually, which you mentioned a little bit about how we talked about in Vivo, we started with the repartitioning and global tables, and we've recently obviously started doing the RPC calls. How have you found it, and how has the experience been of the technical difficulties around that? Because obviously you talked about it's more complex, but how is that in reality?
It was kind of easy to query the data into global tables, and you have everything's there, and it was just 2 lines. But having RPC is a bit more complex, because at first you have to somehow expose your unique endpoints of the application, and then you have to update all the other services you have to make able to call that service. So it's a bit of you have to update everything and have to link everything by RPC. But even if it's a bit complex and more time at first, it is payable. It will pay it back for you.
So what was the issues with the global tables then, using those instead? What were the issues with that?
I think our biggest issue was the increased startup time. So the problem is we have a lot of data, and when each instances have to query that data and they need to process everything before they can start up, it really increased our startup times, which is not it's not viable for us.
Okay, perfect. Any more questions?
Any other questions?
Yeah, I have a question. You mentioned Kubernetes. Is there other basically like technologies that you need that are required to basically spin up a Kafka instance at all? So, for instance, what kind of architectures, what kind of data volumes, what kind of tooling is required, or which necessitates a Kafka event-driven architecture in the first place?
Jamie would like to answer to this because you're more familiar with Kubernetes, please.
No problem.
Thanks.
So I think there's a couple of points there. I mean, we use Kubernetes. We have quite big data processing through our system, and we need to be scalable in response to that, and we need to, our customers expect certain features that Kubernetes allows us to provide, like zero downtime deployments, quite not trivially, but easier than having to write it ourselves and things like that. When you talk about, do you need anything? I mean, you can run Kafka on your local machine. You can run it on a laptop, and it works fine. It works, perfectly fine. You really want a few nodes in there because for data safety, resilience and replication of data, so you don't lose it if one node goes down. So from that perspective, you'd want to have a 3-node machine, but it can run anywhere you want, really. We actually let Confluent, which was, Kafka was created by LinkedIn, but the guys from LinkedIn who created Kafka formed Confluent. It's open source, but they are some of the big contributors, obviously. They host it for us, and we use a managed service through them for Kafka, just because it can get a bit complex managing it yourself, all the the infrastructure side. So it's nice to let someone else worry about that and know you're not going to make a mistake because you're a small team. Data resiliency or something that means you're going to potentially lose data. But otherwise, I think the only thing I'd say is you probably do need a relatively large scale. Otherwise, I'd argue it's maybe not worth the extra overhead versus complexity versus something like either SQL, even like RabbitMQ, that work perfectly well for standard use case. Not to say that Kafka has a massive overhead in of itself, but it's a learning curve if you've not used it before. And there is definitely more complexity to manage than something like Rabbit, where one of the big things in Rabbit is a lot of the things Kat talked about there are because Kafka, you don't delete a message from it when you've read it. In Rabbit, you can read a message and then that message goes away and no one else has to worry about. You don't have to worry about another service picking that message up. In Kafka, you have to partition the data because services are processing in parallel and messages aren't disappearing. So if you just had one unbounded stream, there'd be no way to stop 2 different services picking the same message up twice and processing that same message twice. And if that message is send an SMS to one of your customers, that's going to be annoying. If it's charge them £1,000 on their bank account, that's going to be very, very bad. So you've got to be really, with Rabbit, you don't have that problem, but Rabbit doesn't necessarily give you the same throughput limit, mechanisms that something like Kafka does. We can hit, I've hit before with low latency when you've got co-located hardware, you can hit 1 million messages a second on Kafka. Even with our stuff where we're not, we're running in a more productionized manner where you've got replicas and things like that in place, we still can hit 100,000 a minute, which is orders of magnitude more than we were getting in Rabbit for similar. And not to say Rabbit was giving other things, obviously, for that, but there's a lot more back and forth with Rabbit because of how it works versus something like Kafka. But that does mean Kafka has more complexity and more room for failures and more room for things to go wrong if you're not careful. So from that perspective, I'd say it's not really worth it unless you're dealing with enough data that it matters. But if you do need it, it's one of those things that it'll save you a lot of time versus trying to build the same thing in a traditional system, which is kind of what we had when I first joined. We were struggling to process data fast enough to be, we had to start doing it was basically taking shortcuts at that point.
Sure.
Any more questions from anyone? Brilliant. Rich will be happy he knows what RPC is now that we've been talking about for the last few weeks.
100%. All makes sense. Thank you very much.
Thank you, Katza.
Thank you too.
Definitely learned a lot from you today.
Yeah.
I think
Great.
the presentation was very skillful as well.
Yeah, very good.
Yeah.
Thank you, and thanks for your time and for attention.
Thank you.
Thank you, Katza.
Thank you.
Thank you, Kata.
Okay. Should we take a 5-minute break? Does everyone use the toilet or have a drink or anything, and then we'll start with our next talk.
So,
They want a drink or Coke or anything, Rich?
Fine, actually. Yeah. Thank you.
Yes, we've got a HDMI or it might be able to jump on the Teams call so you can share with the guys over there. You can also plug into the TV if you want. There's a HDMI, or USB-C connection, so it's up to you.
But will they see it?
Yeah, the probably best is to join the Teams call. I've put on the chat on the meetup. I can send you that again, but it's on the meetup. If you join that, you can then just share with these those remotes. And if you want power or anything, we can play it. Yes, fine. Okay, it's fine. I will play you some room. I can take this place.
Every stuff. Is it? Oh, okay. Who would that get to? Hey? And it's got the press dog. Alright.
I don't know if I can put it in, but I know how to do something.
Ah, not bad.
Here.
Can I get the website?
I don't want to be non-professional. I'm sitting.
Don't worry.
Sorry.
I've done a lot worse. And then I've nearly broken my stormtrooper several times.
Several times.
So is that 1-0? There we go.
Password is there. Yeah, which one? Oh, it's the
That was like mine, yeah.
Yeah.
VBA? VBA P.
That would be able to see these probably.
Has to be.
Yeah.
It's VM5D F. Suggest that's not the password.
God, you've got to be on that. I think you'd be on that. I thought you'd be in straight in. Yeah. Come on. Yeah, look at that.
Yeah,
Nonchalant.
this one. Thanks.
Using the backboard as well. It's a new technique in this office. Just like flush. Huh?
Business tactics.
Here we go.
Did you miss it?
No, got it in.
Miles away.
Huh?
Nice.
That's the thing, we're only getting half the action. We can't see the hoop.
I know, but hear the swoosh and hear. Oh,
You could just tell us it was going in and we'd believe it.
Next meetup, we'll get to the camera this way.
that's the problem. It's stealing.
You need to put it there.
Huh?
You need to put it a bit lower.
A bit low. I'm all right with it.
Low and flat. Too much backward.
It's going to be.
Too little backward. Right.
Come on, this is going to happen. Everyone loves to try. Yes!
That's it.
Really, it is, it's definitely a challenge. The challenge. I think I might start playing more for money. That's the one.
I really hate that.
That's the one.
Oh. Yeah, that's.
You have to adjust to this setup, don't you? It's not quite.
Yes, you've got it now. You're another one. Yeah, go on, you go. Go on.
Okay. This is the last.
Let's get again, sorry.
Sorry.
That was the last one. But you are professional.
Yeah. I mean, it's the second week, so I
Go on,
was.
Jamie. Yeah.
Jamie, I think we've got someone else joining the meeting.
Yeah, it just, yeah.
Oh, right,
quickly.
right.
I'm usually, they like it. Oh, lost my,
Do that, Rich.
Ah.
It's been practicing all day in prep for this.
I think it should be better here.
Yeah, it's hot.
What's it? I think we should take the whole time, really.
Just tell me. Right.
I can see those people joining and say, this is not the meetup.
Yeah, this is right.
Yeah, I think I'm ready.
Oh, we're back in there now, back on the zone.
Yeah, I think we're all ready. It's all right. It's all right.
No worries.
Sorry,
I'm sorry, we've got spectators on the basketball court.
Yeah.
Yeah?
So.
It's like you've got ringside seats.
Yeah, the closer ones, yeah.
Huh?
Ah, Rick.
Yes, I said, I think I've got time to now.
No.
Can you offer this guy a job so I've got someone to play basketball with, Jamie? Yes.
It's a nice ball. It's a nice ball. Yeah, it is.
Amazon.
Like balls, there's a brand called Morgan.
Right.
As a silver. We have other ones.
Oh, right, okay. Jamie, get on Amazon, get 5 of them, please.
What?
The leather balls. We want the leather ones.
These level. Okay, are we ready?
Yep.
Set it here.
It might be better for me to stand up. Yes.
Let me just turn that around a little bit as well. So, yeah, is that all right like that?
Yes. Start the timer.
It's okay, I don't have meetings yet.
Yes, welcome to my presentation talk. And first, thank you for hosting me actually. And I think it's the first time for me to join a physical meetup after the pandemic.
Yeah.
And it's good to be here actually, as I mentioned you. Yeah, I will be mentioning about distributed transactions in Service Mesh today. Hope you enjoy it. My name is Alper Sanavci. I'm a software developer at Hazelcast. I know if you heard of Hazelcast before. It's a startup, actually, tech startup right now. We have more than 150 employees, and half of them are actually technical guys. I'm working there for more than 6 years, and now I'm working in the cloud native team. I started in different teams, but we are mostly working with the Kubernetes and the containerization issues within Hazelcast, and also discovery mechanisms. I love to solve problems if I can, of course. If you would like to reach me, you can always send an email to alparslan@hazelcast.com. By the way, about the talk, you can always interrupt me. I like to be informal, actually, not to directly talk a lot. So feel free to interrupt me and ask questions, or if anything is not clear, or if my English is not clear, since I'm not a native English speaker. So please ask any questions if you want. So let's imagine first, start imagining. Let's imagine that we are running a large e-commerce business. Okay, we are not running, but we are working for a large e-commerce business, and this e-commerce business can have thousands of transactions per day. It's a real large one, and there are a variety of goods sold in this online actually, and by meaning variety of the goods. There might be multiple channels for sales, multiple different websites and so on. And the locations can be different, the time zones can be different. So we are thinking about a really large business. And imagine that you are a developer in this company, with which you have near 100 of IT workers. And there are multiple specialized teams, and they might be located in different locations in the world, and some of them might be working remotely. So we are thinking really a global company right now. So in this company, the CEO or CTO comes to you and asks you this question: how do you set up the software architecture of our company? Just imagine that. So, what will be your answer to this question? Maybe just in a few words, maybe what the keyword will be remaining. What the keyword will be in your mind first?
Availability.
I think from the architecture point, we will have, especially nowadays, actually today's, we will have this comparison, the monolith application or the microservices. Of course, when we talk about this large business, this large application, monolith architectures are not feasible, we can say. Eventually, you will come into the microservices architecture, because you will need scalability, you will need fast upgrades, fast updates of your application, and also you have specialized teams. So microservices will be much more easier and better to maintain. So what about what's bad about monolith applications? I think you already know, but if we repeat it, they are too large and complex. Right, and you put so many functionalities in them, and they are also difficult to scale because most of the parts of or modules of the monolith are not idempotent, so you cannot easily scale them up. And also you have really slow startup time. So if you accidentally or purposefully shut down the application, it will be really difficult to start it again. You all remember in previous days, actually, we had these maintenance windows. The companies were saying us, actually right now banks are still saying the same words, but especially in the other companies are also saying, the other businesses are also saying that we will have some maintenance window, and then you cannot access the website these days. So yeah.
So many of our competitors still have that thing of, you have to, oh no, you can have these hours where we're not available.
Yeah, that's what, but if you think that,
Microsoft Dynamics is maintenance windows, it's crazy.
Maintenance window once a week, right?
Yeah. But if you think of this large e-commerce businesses, if you have, for instance, 1 hour, even 1 hour maintenance window can make you lots of money, right? Lots of value. So also another problem is the on each update, if you have an update to your application, you need to redeploy the whole application at once again each time, and so on. Actually, there are many different issues with the monolith applications, especially if you're a large organization. I need to also say that here, if you are a small business, if you are a small company, and if you are a little small team, microservices can be also bad. You know, monolith might be a better approach, but we are not talking about the small ones right now. Actually, most of the people are right now saying that you can start with the monoliths, and eventually, if you are big enough, you can have a transition from monolith to microservices, which is also a difficult process. Also, there's another issue over there, but that's not our topic right now. So let's continue with the microservice architecture. Then you choose the microservice architecture and you start building the whole application, the whole system with microservices. But it is not the end of the story. Actually, your story is just now beginning, because with the microservices, you will have lots of issues coming with you. For instance, yeah, you can just imagine this picture. This is just a sample picture. This is not the origin. This is not a real application architecture drawing. But let's imagine this one. You can see that there are lots of context services, lots of backend services, lots of resource points, system of records, message broker, Kafka, such as clients. There are many different components and services together. And if you get this picture, and if you add more and more components day by day, since you are a growing company, then you will have more problems in your architecture, in your system. So we also need to mention that, yeah, these words, Docker and Kubernetes, are the most popular words, right? You know, these days actually we're hearing these words a lot. The microservices right now, it is the best way to run the microservices are to containerize them. Then of course Docker is the most popular right now. And then run them in the Kubernetes environment, which is a container orchestration application, actually, environment. So most of the time, you will build your microservices, containerize them, and then deploy them to a Kubernetes environment, which wherever it is actually, it might be a managed Kubernetes, it might be a dedicated Kubernetes environment, but yeah. And then you deploy your microservices to the Kubernetes environment. But when you get the hundreds of microservices, actually, for instance, I can give you an example that from a use case, a real use case. I know a business, actually, an e-commerce business, actually, based in Japan. I cannot, I not give the name directly, but they have more than 250 microservices deployed on Kubernetes, and then in this one actually they are having more than thousands of pods running together at once. So just imagine that you have 250 microservices, and you just need to handle them very well, and you need to monitor them, you need to maintain them. That's really a difficult process if your microservices are increasing in number. So this to solve this problem, service mesh comes in actually. What's a service mesh? Actually, it's an infrastructure layer that enables secure source communication. So you have the microservices deployed on Kubernetes environments. So you know that the microservice can be implemented in different languages. It's a polyglot environment, so you can have Node.js microservices, Java microservice, or Python microservices. So to communicate between those services, you need to have a really standard approach to communicate, provide the service discovery, to the security, to trace them. All of them should be standard. So to make them actually, there's actually this started with the Linkerd, and Linkerd, the guys that built Linkerd thought that We need to implement such an infrastructure application that can manage the traffic policies, especially among intra-cluster traffic policies, and the security and the observability. So we can say that the service mesh does these three things is in general. Actually, there are many other features, but in general, we can say that it manages the east-west traffic policies, actually, not north to south. I mean that it's not something like an API gateway. You don't think about the ingress. Of course, Istio and other ones also provide some ingress features, but the main focus is the east-west communication. And also they provide out-of-the-box security, and also you have some observability features such as directly monitoring the communication, they directly having the number of success and failures. You can directly observe them out of the box. I will come into the structure. Actually, the architecture of the service mesh is generally, as you can see here, there it states a control plane, and over this control plane, there is a data plane. This is called data plane. This part, this data plane.
Sorry, that's a question.
Yeah, sure.
When you talk about like the managing of the traffic, obviously is one thing. When you talk about security and observability, is a service mesh handling that context? Is it all about communication between the services, or is it handling actually the services themselves, like observability as well? Or
not the services, because actually to make
still rely on Kubernetes, for example.
Yeah, for instance, you have Prometheus or some kind of other tools to observe or monitor the services themselves. But since you are monitoring the communication, actually, you can also say you're managing, you are observing the whole application, eventually you will get the information. As we said, actually, the data plane consists of the services themselves, and most of the service meshes have sidecars as the proxies, as the sidecar implementation, sidecars on the Kubernetes pods. And these sidecars provide act as a proxy, and then do the communication between services, perform the communication, and also they communicate within the control plane to provide the information about the services. I will come to this picture again to give the details. So what are the service mesh products, available ones? The most popular one, most likely you heard of it, Istio is the most popular one right now. With Envoy, they are using Envoy as the proxy. HashiCorp's console is also a popular one and getting popular day by day. Linkerd is the first service mesh, actually, featured service mesh. There are also other products similar to service mesh, but the service mesh is first used with Linkerd, and right now they have released Linkerd 2.0, which is the totally different product from the 1.0. So these are the top three are the Istio, console, and Linkerd, and we have also the other ones, the Kuma, Open Service Mesh, and App Mesh, and there are many other service meshes, but these are the most popular ones. We will continue with Istio. I will make a demonstration on Istio. So we'll come to the details. So when do you need the service mesh? That's the question, because as I mentioned in the beginning, you might not need the whole microservice architecture on your system, on your application environment. And also service mesh is the same, actually, when we think of the complexity. Because here, this is a really great graphic. I got it from the Nginx website, actually. It's a really good representation of the how you get the complexity versus the cost to operate. So the horizontal axis, the x-axis shows the complexity, interdependence, and speed of change. So when you go to the end, you will have many complex interdependent apps. So you have lots of microservices if you go this way. And if you go up, of course, the cost to operate is increasing. So if you have a single simple app, then it is much better to use native Kubernetes Pro and services. So it is better to use just write your microservices, deploy them onto Kubernetes, and do the checks or do the required features by yourself, making it native. But as your number of applications increase in time, and also if the complexity of if your architecture increase in time, then you will need some more specific product to provide these features that are provided by the service meshes. So at this point, for instance, this is the, of course, an abstract point, but at some point, the service meshes costs are much less than the native Kubernetes Pro and services cost. So we can say that you need to use service meshes. It is not something like that. Service mesh is not something that you will just install it and it will be easier to manage. It has some costs to operate actually. Yeah, so we have the microservices, we have the Kubernetes environment, we have the service mesh, and we installed service mesh, but we have still need to resolve some more issues. Since we are not running the monolith application, we have multiple services, multiple system of records, as we mentioned in the beginning. But you need some transactional operations on your environment, especially since you're an e-commerce business. Then you will do most likely, especially when doing operations with third parties, you will do some transactional operations. So you need to prepare yourself to distribute transactions because your environment is distributed. So you need to think about them. Our basic problem is actually the dual write problem. What's the dual write problem? Let's imagine that we have this sample application. Let's say just a sample part of our e-commerce business. So this one is just presenting the purchase of a product. So there's a front-end service, and this is the providing the information to the user. The user queries the front-end service and tries to buy a product. And when they want to buy the product, our front-end service need to communicate to 3 different services. First one is the user service. Actually, these are the updates, not the write ones. It needs to write the user service. It needs to write the product service. Also, it needs to write the banking service. So these all 3 needs to be done in the same transaction boundary. So we need to do it atomically. We can say that it should be atomic, consistent, isolated, and durable. But let's say that just the transaction boundary right now, and it should be just in one transaction. So if we have an issue in one of them, for instance, let's imagine that we have an issue on the banking service, then the other ones, the other updates, the user and product updates should be rolled back. They shouldn't be persisted, or they shouldn't be stayed as they are asked or queried. So let's show this one on this environment. I have a Kubernetes environment deployed on GKE, Google Kubernetes Engine. So I have nothing right now. Let me first try this. You will see just the regular Kubernetes services running on the default namespace. So to deploy it, actually, I have just a sample application. I will let me show you here. Yeah, here this is my deployment. Actually, I will have the user service. There will be only single replica, and this service for this deployment, the user service deployment, the service, and product service, banking service might be a bit. Yeah, let me increase. I think it's easier, right? Yeah, it's better. So we have the user service, we have the product service, and we have the banking service. These are just, and also have the e-commerce service as the front-end one. They are not, they don't have any connection to a persistent database, but they have their own internal data stores, just as a demo. So let's deploy this one first. The user service, product service, banking service, and e-commerce service. And let's check the services. Yeah, right now you can see that there are 4, other than Kubernetes, we have 4 services, and only the e-commerce service has the load balancer type, and we will have the external IP when it's assigned, actually, since we are waiting for it.
So then you have 4 services running.
Yeah, we will also show. I will also show. By the way, in this Kubernetes environment, the Istio is installed, already installed. So I can also show you it's installed. This is the Istio site system namespace. So yeah, you can see that the KLA collector, Prometheus, egress, ingress gateway, and Istio-D are already running. So let us check the KLA. I think it should be here, but okay, the KLA console. The KLA is actually the basic out-of-the-box monitoring service, monitoring application. So we can check the graph here and see the service. I don't know all this one. Okay, since everything's idle right now, we need to do it, but if I can, okay, here. Yeah, you can see that the services are here, the product service, user service, and e-commerce service. The other ones also the workloads. So we will see the pods also. Let's also check the pods. Yeah, we have only 4 pods right now, and you can see that this is the they have 2 containers in the pods. One of them is the actual application, and the other one is the proxy application, the Istio's proxy envoy actually. I can also show you that the details. Let's describe it. Let's check one of them, and you will see that. Yeah, here. Yeah, there are 2 containers. One of them is product service, and the other one is Istio proxy. So right now, let's also check the services and get the external IP is assigned, so we can access our application using this external IP. Let's do it here.
So you have multiple services running across 2 containers.
Yes, exactly. So actually, we have the same. Let me show it again here. The same structure as it is actually right here. Mm-hmm. This is the e-commerce service, and the other ones are the same: the product, user, and the banking service.
Yeah. Yeah.
And you will. I think you can also see it right now. Let's increase this one to 1 hour.
So is there any sort of GUI for Kubernetes, or is that?
Yes, this is. You can think that as a user interface for displaying these services, but it is provided by the Istio. It's the service mesh itself, because it's checking the communication between them and then providing the information. So this is actually a sample application, and you can see here that we have a single product, a smartphone, which is the price is £4,500. The important part is actually here the product stock. It is 10 actually, So this means that we have only 10, and this will be updated by this number is actually taken from the product service, and this information, these two information is taken from the product service. And I also would like to show you this. Take your attention to this part. This is the available user credits. Imagine that you have some voucher codes, vouchers, and then you apply your as a user, you use them, and you have now available user credits of £10,000, and this is taken from the user service. Okay, so let's try to purchase this one. Yeah, this is our basket, and we will get how many we will get. For instance, let's say that we'll get 3 of them. And it's asking us how much you will spend from your credits. Let's think that we will get 5,000 from our credits. So the remaining 8,500 will be taken from the bank account. It means that it will try to communicate the banking service. So let's try to buy now.
Is that why you couldn't do one, then the other, than the other services? Because if the bank failed, you don't want to do credit either.
Yeah, exactly. We will see it right now.
Yeah.
Actually, right now, what will happen is the banking part, the banking service will give an exception. It will give an internal server error. And actually, let's check it. Yeah, we will get the internal server error. Okay, this is just, of course, it's not a good one, but to show the user. But we got this one. So what you expect? So the other two operations, the stock update and the user credit update should be rolled back, right? And let's check you can see that the product stock is 7 and the available user credits is 5,000 right now. So we have a problem here. This is the dual right problem. And also, yeah, this is a good representation. And you get you can see that our e-commerce service, I don't know if you can see it, we can make it a bit larger. Our e-commerce service is trying to, this is the workload, and it is communicating to product and user service. It didn't take the banking service yet. I think in the next update, or if updates later, we will get the banking service. You will also see that the e-commerce service is trying to communicate to banking service. So we got our problem. Continue the presentation. Yeah, this is our problem and how we need to resolve this one. If you have the monolith application, this will be easier, right? You will be in the same application runtime. You can just try to, you will have the asset databases, and you will easily do the transaction. But in the distributed one, you have different applications running in different parts of the environment. So there are two main approaches right now. Actually, there are more than 2 approaches, but these are the main 2 ones. The first one, most likely you heard of it, two-phase commits. This is the kind of old one. It is, of course, still used in many parts, but the part of, you can say it's a bit older. So in this part, actually, you have a coordinator that coordinates the transaction itself. As you can see from the name, there are 2 phases of the transaction. First one is the prepare phase, and second one is the commit phase. When the front-end service asks to start the transaction from the coordinator sends the prepare message to all of the services. The services prepare their logic, their business to run the transaction. If they say okay, the coordinators then sends them the commit message, and then they commit. So this is really a long and blocking way of doing the transaction, and this is mostly not preferred way of doing the transactions in the distributed environments. And if we have, again, a failure, or if we get the problem on the banking service, the coordinator can try to roll back from this event logs, and try to update the user and product service. When we come to the pros and disadvantages, or advantages and disadvantages of the two-phase commit, yes, the the biggest advantage of two-phase commit is actually two pieces. Actually, it's a strong data consistency. You have it. You don't, since it is running blocking. You will get it actually all or not activity. So it is running automatically without any issues. And you will have the read-write isolation. So nobody will see the uncommitted writes from when trying to read the information from the services. But there are many problems. The first one is the blocking. As I said, this is running blocking. So it is if one of the services is taking so much time, your application should wait actually. And also this might affect if you would like to, if you have some ordered operations, then it will be much bigger effects. Another issue is the data sources should be XA compatible. And you know the NoSQL databases are not XA compatible. So that's another problem coming with the two-phase commit. And you will have scalability issues because of the coordinator. Your coordinator will be the blocking point, the neck of the problem. And also you will, if you have coordinator failures, then there will be another problem on your unfinished transactions. So what we have instead of what can we do instead of two-phase commits? Right now, what is getting popular is the distributed sagas. Maybe you have heard of it, I don't know. But it is kind of more available, less consistent version of the two-phase commits, we can say. So what happens here is that actually we have, again, the front-end service and the other services, but each service is responsible of its own local transaction and needs to communicate to each other to coordinate the transaction itself. This might be done by using some event sourcing mechanisms, or there might be some orchestrator applications, you mentioned that. And if there are any issues with one of the applications, one of the services, then they will send the compensation calls. The red ones are actually mentioned, the red compensation calls. What are compensation calls are that they are semantically rollback functions of the actual functions. Well, imagine that you update a database row with the compensation, you can overwrite that one, or you can try to roll back that one, or you can add another row that overwrites the previous one.
Like correction in order.
Yes, correct, exactly. Correcting the stock or the orders or the information. As I said, the compensation actually is equals to semantically undoes the action, the actual action. Actually, this picture is actually a better representation of the saga, especially if you think that your actions are, your operations are in order. That will be easier to understand. Because, for instance, imagine that you are booking a trip and you need to first plan the meeting and then book the flights. If flights are booked, then you need to book the hotel, and if it is booked, and then you need to book the transport. But if you have any issues on one of them, for instance, if you had an issue on when booking the hotel, you will cancel the hotel booking, and then you will cancel the flight booking, and then you will cancel the meeting plans. So this is a sample representation of a single saga. There are two types, mainly two types of distributed sagas. Again, there might be different implementations, especially on how in-house implementations of saga might include lots of different architectures, but mainly there are two different architectures. One of them is the orchestration, the other one is the choreography. In the orchestration one, you will have an orchestrator similar to coordinator in the two-phase commit. You send the transaction information to orchestrator. This orchestrator mostly is the starter of the transaction. For instance, in this one, most likely the plan meeting will be the orchestrator and coordinates the transaction, the saga. In the choreography one, it is the responsible of coordinating the transaction is distributed among the services. Most likely they are communicating through an event sourcing mechanism. So they are sending events and listening events from the source. So over there, they take their own action and decide if they would like to continue, commit, or cancel or call the compensation action.
You don't necessarily have to couple those services together. You can just have an issue event saying I failed to take a transaction.
Exactly. Yeah, you can just publish, broadcast your message as I'm failed actually, and then the other ones take the action or not. That doesn't depend on it.
So the hotel booking service is just watching to say if the financial service fails, I'll revert my hotel.
Exactly. That's the point actually. That's the point of the choreography part actually. But with the choreography, it is nice to have this. You don't have the single point of failure, but the problem comes with the debugging and the maintenance problems, because you cannot. If you have an issue in the system, it might be difficult to see the whole picture. But as I said, there are different mechanisms to get the positives of the advantages of both approaches, orchestration and choreography. For instance, you can have some other applications that are also monitoring the event source and trying to give you a picture of the transaction state. But we don't need to mention those details here. So the positive parts of the distributed sagas are it is running asynchronous. You don't need to wait for the other, especially the third-party applications to complete. And also it is heterogeneous, it is suitable for heterogeneous distributed components. You can have any type of application, any type of language implemented application. And also you don't need the XA transactions, which is really good. And of course it is scalable because it is running distributed. The problems, yes, you will have eventual consistency. You don't have the, this is the drawback, the main drawback. It will have the consistent at some point, but until coming to that point, you might have some inconsistent states. Also, there will be no read isolation because all services are running independently. They might update here. For instance, when the saga is running, if you try to check for the product stock, you might get the lower stock, but the banking service might not be updated yet. The compensation function development is also another issue because you need to find a way to undo the operation. And if you need to implement that function in-house, you need to implement that one. You cannot, it's not something like you call the rollback function and it automatically does the rollback. And if you have the compensation failures, there will be some problems because either you will have compensation of the compensation functions, but there will be another problem. It's not a sustainable one. So there will be some issues over there.
Would you still use this mechanism if you like communicating with third parties and things and integrations? I mean, obviously that includes another level of risk to it, I suppose, but.
Yeah, of course, but these ones actually are mostly suitable, especially the sagas are mostly suitable for applications that, how can I say, you don't need, you will need more availability than consistency, then it's okay to use this. But if you need the, as you said, actually, if you're a banking application and if you need the strong consistency to provide information on each channel, then you will need to use some other things similar to two-phase commit, or you need to do it in monolith way, not microservices. Actually, this is the main issue with the banking. Actually, I can definitely say that this is what we are facing with the financial companies. Actually, the financial sector, they are really coming from back, as from the technology point of view. They have lots of money, they have lots of funds, but it's really difficult to do the improvements on the financial sector. Yeah, let's talk about our solution. So this solution, the solution I will provide right now is not a production-ready one. This is not the production-ready solution of Hazelcast provides. That I will just mention how what we can manage on service meshes, what they will provide us about the transactions. So let's talk about Istio architecture first. Go deep dive. As we mentioned, actually, there are two planes, the control plane and the data plane. The control plane has the coordinator applications of Istio. Again, these are microservices, by the way. The Pilot, Citadel, and Gale, they're all microservices running in the Kubernetes environment. They provide the discovery, configuration, the certificates, the other the features altogether. And on the data plane, we have the pods. These are these gray squares are the pods, and each pod actually have two main container. One of them is the main service container, the application container, and also we have the proxy container as sidecar. And as you can see here, this service is not communicating directly to the other services. It is only communicating through the proxy. And the intra-service communication is provided by the proxies. So you can see that the mesh traffic is east to west traffic is actually done between the proxies using the proxy communication. So this is the first part of the architecture. The second part, we will need to talk about the filters, because in the solution I will use envoy filters. As mentioned here, actually we have the proxies, and these proxies are envoy proxies in Istio service mesh. And what we have common with envoy proxies, it has a great feature called filter chains. So between the listener and the service, actually the proxy listener and the data service, there's a number of filters that you can put, and you can enrich the data using these filters. These filters can enrich the data on the HTTP level or network level or security level, but you can add as many filters as you want. But of course, adding more filters mean less performance. But you can, what you'll have is actually you will grab the data on the fly and you can do whatever you want. And we will use the we will implement a filter to implement the distributed sagas. So this is the architecture of our application solution. So again, we have the three service pods: user service, product service, and banking service pod. And they have the envoy proxies, as you can see here. And we will add a filter. The solution that I mentioned is called Propeller. We gave them the name Propeller. So we will add the Propeller filters to envoy proxy. And these Propeller filters will communicate to our application, which is called Propeller application. It will collect the information about the transactions, the sagas, and it will provide the compensation and the other variable information again to the filters. And it will use Hazelcast cluster as the storage, actually, because Hazelcast cluster will be a distributed storage, in-memory storage, and it will be really good for scalability and especially cloud-native environments such as Kubernetes. So let's see how it works. Our application is running as we did in the previous one. Right now, I will first here. I will create I will deploy my application. We will have a stateful set with 3 replicas. This will be the main Propeller application. And we will also have the Hazelcast cluster. This will just start a 3-member Hazelcast cluster. So let's start the Hazelcast cluster first. Yeah, and let's also deploy the Propeller application. Yeah, we can check the pods and services. Yeah, we have the Hazelcast cluster service and also Propeller application service. Let's check the pods. They're running okay. Yeah, we added 6 more pods, 3 for Hazelcast cluster. Each of them are running Hazelcast instances. And we had 3 Propeller applications. They are not. You don't need to add 3. This 3 is not requirement, but just to show actually is the scalability and distributed structure. I made 3. And let's check one of their logs to see if everything is running okay. Yeah, everything is running fine. It's a Spring Boot application, and it connected to the Hazelcast cluster. You can see that there are 3 members in the cluster, and it's running a Hazelcast client to connect to the cluster. So everything is running fine. And if we check let's stop this one and check the console. Yeah, you can see that the cluster is here. Hazelcast cluster is running here. The Propeller app is connecting to the cluster. Right now, there's no communication between e-commerce and other services and between the Propeller app. How we'll do the communication is we will apply the filter. We will deploy the filter. So let's see the filter. It's a just simple application actually. This is just an Envoy filter kind, which is provided by Istio. And this will be, of course, an HTTP filter. We will interact the communication on HTTP level. And the filter is written in Lua. So it is just an extension of Envoy itself. And here you can see that we have 2 different functions, actually 2 different listeners. The first one will be on request. On each request, we will call this function, and on each response from the service through proxy, we will run this one. What we will do here is actually, if there is a transaction ID provided with the application itself, we will just save it to Hazelcast cluster. Actually, send it to Propeller application, and Propeller app will save it to Hazelcast cluster. And on response part, if you have any issue, if you have any status other than 200, if you have any failure status in the HTTP level, we will just get the compensation action information from the Propeller app and call the compensation actions. So yeah, let's. Before that one, I think I need to show. Let's do the demo, and then I will show the compensation action run. So let's run the kubectl apply Propeller filter. Yeah, let's check and get Envoy filter. Yeah, our filter is now deployed. Let's see the details. Yeah, our Lua code snippet is here. Yeah, let's also see the console. If you have anything here, I think yes, that's fine. So we can again make our original demo again, and we will see if the Saga works or not. So we have 5,000 available user credits and product stock as 7. So again, we will have 3 and 5,000. If the Saga doesn't work, hope it works. If it doesn't work, we will see 0 as the credit, and we will have 4 as the remaining stock, right? We are buying, again, the error occurred, and we go, yeah, we have the product stock 7, and we got the available user credits as 5,000 again.
So rejected.
Yeah, because in the background, what happens actually, let me show you in the background, what happened is actually, we got the HTTP 500 from banking service application, the Envoy proxy intercepted, and our Propeller filter asked the extra Propeller app the details of the transaction, and then get the details actually. What I mean by details is the addresses of these pods, which applications are run in the transaction, and which parameters actually, because the parameters are also important. So it gets those information and calls the compensation actions. So this is kind of orchestrator approach, because still we have the single point for the storing the transaction data, but the transaction, the compensation actions are called from on the action on the services itself.
And those services are actually coupled because they don't have to know about each other technically, is that right?
Sorry?
The services themselves aren't coupled because they don't technically know about each other, it's just the envoy.
Yeah, yeah, exactly. And here you can see that, I think that will be much easier to see from here. The e-commerce application try to connect to user service and product service, which has the green ones, they are successful. But for the banking service, since it is showing red, actually this one is right now gray, but since it is not calling it right now, it's in the past because of we are seeing it gray, but if it once continuously, you'll see it red. The banking service failed. And what happened is actually our propeller app, we cannot see, of course, the filter communication, but our propeller app actually, let me also show the idle edges. I think, yeah, this will be much better because you can see that our banking service before, not right now, when the transaction happened, tried to call the banking service itself and also the user service and product service with the compensation actions. So we can see it also here. Yeah, that was the demonstration. So what next? Yeah, as I mentioned, this application is not, the solution is not production ready. There are many flows actually. I won't mention them here, but there are many flows in this one, such as what happens if the filter had a problem when the compensation calls are called, or the whole application crashes. What happens? There are many issues. But actually, in Hazelcast, we are now working for a solution using these distributed sagas. It will be the orchestrate approach. It's now internally called, we call it Turbine project. It won't, I think it will, the name will change when we publicly announce it. But it will be a application toolkit. It will be running on the application level. It won't be running on the service meshes. It can run with service meshes, but service meshes won't be required to run it. But it will be providing applications a distributed Saga environment, and also you can get the ease of service discovery and other features with that one. So yeah, in future, hopefully you will see some solutions directly from Hazelcast. Yeah, that's all. If you have any questions, I hope it is not so boring.
No, very interesting.
I have a question. Yeah. So, what languages were you using in these examples? Like you mentioned Lua at one point, and you mentioned the YAML as well.
Yeah, for the services actually, for the service itself, you can use any language. You can have, because we are not directly running our transaction on the application level. We are running it on infrastructure level.
Yeah.
So the services can be written in any language, Node.js, Python, Java, or anything.
Yeah.
But our application is actually written in Lua, the propeller filter. But Envoy actually, you can have WebAssembly. You can use WebAssembly, C++, and Lua, and a few more extensions when writing Envoy filters.
I use Lua once. It's a nice language with the tables, I think it is.
Yeah.
With the envoy process, just so I understand that, you may have mentioned it, I've probably missed it, but the advantage to them versus just issuing, say, undo events, basically. The advantage to that is that you don't have to worry about, you don't have to know as much about how to undo the, is that the main kind of reason, or are there other values there? Is it that you don't have to couple your services as much around knowing how to issue the undo event, or is it more around just, is there another benefit?
Actually, the benefit with the filters, actually, you don't need to make anything on the application level to coordinate the transaction itself. Just you need to provide the compensation action, of course, and also what we have it here actually, we need to provide transaction ID to a unique transaction ID on each transaction to get the information put back together actually. But related to the transaction itself, you don't need to do anything. as you see, I haven't redeployed the applications.
Yeah.
The applications were over there. I just applied the filter
Yeah.
and it was running. So
That's it.
yeah, we didn't need to redeploy the applications themselves because it's not left on anything on application level, other than the compensation actions, of course.
Okay, that's good. Really interesting.
Yeah, that's actually, this one is about these demonstrations actually, as I said, this is about distributed sagas, but it also shows what you can do with the service meshes. Actually, they are really providing lots of features with the proxies, with the Envoy proxy, with the, yeah, most of them are using Envoy right now, but with the proxies, the filter level, for instance, with the HTTP level filters, you can have the HTTP caches, the other security features, because you can intercept at any level.
Interesting. I've looked at it before because obviously it's another level of complexity. I had another level of something to learn, but see, even the visualization, right? It's very.
Yeah, exactly.
Exactly.
Out of the box, actually, and also it's really easy to install an Istio on your Kubernetes. You just call the it's a command line application, install it, and then it's ready to run.
Yeah.
Everything you have it. And you run your applications, and your applications also don't need to know about the Istio environment, because again, Istio environment is running on all infrastructure level.
That's very cool. Yeah. That's really
But one of the problems with Istio actually right now, what is discussed actually, especially after some point, after some large applications, it has really big performance issues.
Oh, really?
Yeah, still. And Linkerd is right now actually trying to provide a better solution to Istio, because they implemented their proxy from scratch using Rust, as far as I know, and they are saying that I didn't check the benchmark, but they are saying that they are really fast, especially in the large applications environments.
awesome.
Any questions? Yeah. Thanks, Dan. Thanks for listening and thank you for your time.
Thank you.
Yeah, also, if you have any questions, we didn't ask you online ones.
Any questions, Alison?
A lot of it went over my head, obviously, but I did find it interesting.
Yeah, very interesting, actually, yeah.
Yeah, especially seeing the actual, seeing it all happen.
Yeah, I mean, that alone is a big thing we're missing, right? The visibility of what's actually happening like that.
Yeah.
Is huge.
Exactly.
Yeah. No, very, very interesting to see that, actually. Yeah, visibility is a big part, isn't it? Yeah.
Yeah, like visualizing the problem and solution.
So would you still be saying Istio is the one to look for, or would you be saying if you were looking at service mesh now, it'd be, looking at something a bit more performant? I guess it depends on the use case, right?
Yeah, exactly. Actually, I can say that if you have a small application environment, small application system, if you don't have lots of transactions coming to your environment, I even don't recommend to use Kubernetes.
Yeah,
because first you will need the knowledge base to run it, to maintain it, which is really a costly thing, especially right now, because the Kubernetes DevOps guys are really expensive to hire. But the service meshes right now, for now, actually, if you have just as we mentioned in the beginning, if you have a larger business running, and if you have lots of microservices in your environments, which actually we think that it is not achievable to be the 200 microservices, but it's not that much difficult. If you just start with microservices, you can end up with really high number of microservices in your environments. It's very easy to get those numbers.
It's definitely one big debate of how big a team you need to manage how many microservices.
Exactly.
Yeah.
That's one of the questions.
Yeah. No, it's very interesting. Very, very interesting.
Do you think most of, like you mentioned, like financial firms and stuff earlier on, and how that they seem to be? I got the impression that they seem to be a bit more entrenched with monolithic architectures. So do you think within the next going forward, do you think more and more organizations will move towards microservice structure?
Actually, if you asked this question 5 years ago or 2 years ago, I would definitely say yes.
Yeah.
But right now, you can check on the internet. There are many articles. People are discussing about that.
I've seen.
Also, there are some companies, like
Yeah.
some businesses,
Yeah.
going from microservices back to
Yeah.
monoliths, because as we mentioned, actually, running microservices is not something easy that you can.
Because of the orchestration issue.
Yeah, orchestration and also the number of employees that you need to run with, maintain. That's the basic cost of a tech company, actually. The main cost.
One of the things we found as well is it's the minimum bar you need to have. Now, you can be a senior developer, but if you've not experienced, not done much with microservices, especially with Kubernetes, it's a hell of a lot to learn when you join a company that's using. I mean, if you're using Service Mesh and Kubernetes and Kafka and a lot of these technologies, someone who joins who hasn't used it before has got a big learning curve. There.
Exactly.
You know, it's a big thing for them to learn. Even if it's the people who are there finding it, it can be a big learning curve. For somebody.
Yeah, I met many guys actually. I can directly say that, for instance, one of them said that I'm hired as a Kubernetes DevOps guy, and now the company is frustrated with me because they need to ask everything to that guy.
Yeah.
All the information needs to go from that guy, and if you can of course hire multiple people, but it will be costly. Won't be easy.
Yeah.
I mostly describe as the Kubernetes. This is my description, but it's not a proper. It might not be the proper one, but it's something like distributed operating system.
Yeah.
Imagine that you are trying to run the operating system by yourself with your employees, your developers. For instance, you need to go into the details of the macOS, or you need to go into the Linux details. It's really difficult because you need to get specialized people to get all details. But what you are doing with Kubernetes is that you need to go into the details of the networking. You need to the resource consumption, the details. Everything you need to go in details. It's not something easy. Yeah, the commands are easy. The installation is not that much hard, but maintaining it's not easy. Let's say that. Yeah, I think we're done.
It really is one of the things that gets picked points. If you go on, if you have to deal with all things like maintenance windows and all the horrible things that come with that, but then if you go with the complex and cool stuff, it becomes a completely different set of problems, but still its own problems that you've now made your job much harder.
Yeah. Thanks.
So it's just all about what are your objectives?
Yeah, that's the trick, isn't it?
Organisation.
What are the actual things you need?
What is it that you are trying to achieve?
Yeah.
And then you choose
You're right,
architecture based on that.
Not just
you can't just try and change architecture because it's hard, it's difficult, there's a silo. How many organisations do you go into that are old enterprise kind of, and some guy knows how the old AS400 system works, and he's a silo.
That's true,
and you've got this kind of, this knowledge gap with everybody else in the team. That's where you need cross-functional teams, and you need that kind of constant engagement with everyone. I just think that you choose a technology that fits your objective, and whether or not it's hard or not, that's what you need to do.
Yeah,
that's definitely.
And then you make it work in the best possible way.
You cannot just use these technologies just you want them.
Because you want to tell cool.
Yeah, cool. Let's try to use this.
It's definitely CV driven development where people choose something because it's cool and it looks on CV, and but you've got to look at the problems you're trying to solve. Definitely. No, so that's not really good talk. Thank you.
Yeah, thanks.
Awesome. Any questions then? I think we can wrap it up. Brilliant. Thanks for joining, everyone. Thank you for everyone joining online.
Thanks to staying online, Romania.
Thank you.
London, Australia.
Thank you.
See you tomorrow.
See you all tomorrow. And
See ya. Have a nice evening.
we'll put the meeting on for probably around 10 next week.
Bye.
Night, Kata.
Yeah. That's it. Everyone's
You're talking to the
I know. See ya.
Bye.
Peace out, crew.
Bye-bye.
Bye.
Right. What do we speak to? Is anyone taking it home? Otherwise, we'll leave the room. Rich?
Nice to shoot some hoops with someone
Nice to
who
meet
can
you.
actually play.
Yeah, they do cool. Thank you.
Thank you.
Yeah.
Thank you for the talk. What's that?
Let's keep in touch.
Yeah, no, I was going to say actually, I'll definitely message you tomorrow because that was really interesting. Keep in touch. Nice to meet you as well.
Yeah, likewise, yeah. I'd like to know if you do have the oil available.
Yeah, I'll talk tomorrow. I'll give you a message.
Take care.
If you
Have a good day.
email Jamie,
Thank you so much for the
I'll message you on meeting.
See you guys.
Details.
Will you be able to find me? I'm sure you should be
You
able to.
message me on meeting from the organizer, so just
Okay,
message me on the meetup app. I'll
okay, cool.
yeah. Right, so thank you.
Yeah, you too.
See you.